So support vector machines is the topic today. What we will learn is this usage of same linear model that we were extending from the realm of regression into classification W transpose X plus B. We learned with perceptron and then extended it into logistic regression case. What's left there, what do we need a little more of classification, is this keyword Hinge loss that we will get to know today. So what's absent in logistic loss that we need this one? We will get an intuition of both the geometric and functional definition and interpretation of the Hinge loss, which is tied to the concept of margin, which is the basis for support vector machines. And the whole idea is based on constrained optimization. We will do some exercises to freshen up our memory on the idea of minimizing a function that is restricted or subject to some other functions or constraints. And based on that, we will define and derive optimal margin classifier, which will lead us to this new word, support vectors. What are those? Why are they needed? Why do we call them support vectors? Is today's agenda. Starting with the binary classification. Again, two classes. We know there is a hyperplane or a line, linear hyperplane, W transpose X. To the right of it is class 1, to the left of it is class 2, because W is perpendicular to the boundary that we are looking at. So what's lacking is that, number one, there could be multiple different lines. How about this blue line or this red line? Perceptron can, depending on the starting point, can reach to any of these three lines. And which one is better? Which one is not good? Apparently, the blue one is giving almost zero distance from this data point. Red one is giving almost zero distance from this data point. Number one. Number two, the points that are far away from decision boundary, they will give the loss is same for the point that is over here and the point that is over here, the loss is same. We use step function, if you remember. On the right-hand side, W transpose X is greater than 0, we say it's class A. But how about for this point? This is far from the decision boundary. This one is very close to the decision boundary, but for both, the loss is 0 because they are correctly classified. But if they are incorrectly classified, the loss is still 1. We don't look at the distance, right? So two things that are lacking in perceptron or a regular linear solution are the, number one, they are oblivious to the closeness of these data points that are almost on the boundary, and the distance is itself. So the loss function, it's kind of ignorant of the reality of distance from the decision boundary. So what do we have? Usually in case of regression, we squared the difference between truth and estimate, prediction and actual value. And if in case of binary classification, we take this as our loss function. Good thing is it looks convex, but even the better we do on our estimates, it's still creating loss on this side. And for the other class, we will be getting loss. The farther the point is from the boundary, the higher the loss will be. 10 points. For 100 points, it will be 100 square. So too big a value. So this doesn't make sense, right? What else can we do? We can choose to have an intuitive derivation of our W transpose X. If we multiply it with minus Y, in that case, the maximal value between 0 and minus Y W transpose X can give us a convex function. So the farther we are from the data point, and if it is misclassified, the loss will be higher. Otherwise, loss will be 0. But here we have a degenerate case again for Y when W transpose X is 0. For the points that are right next to the class boundary, the loss is 0, which is again lacking one of the points, even though we have kind of convex function in terms of this degenerate loss function, but it doesn't care about points lying on the boundary. What we really want is that we want to create a small penalty for being too close to the boundary. So we can say that instead of minus y multiplied by w transpose x, we will say 1 minus y multiplied by w transpose x will give us this function. So original value and the prediction, the loss will be, it looks like a hinge. That's why we call it hinge loss function. Last session, we looked at the logistic squashing function that takes your estimate and squash it on this S-like curve, sigmoidal curve. So W transpose X is interpreted in terms of this sigmoid function. Today we are going to look at this one. If the point is giving very near to the class boundary, we are going to have some penalty, small little loss for that. The geometric interpretation for this particular hinge loss could be looked at using these two dotted lines. The W transpose X is the boundary that we have here. And given the points or nearby points, we can use their nearness to create a buffer, a cushion, a buffer to make possibility of mistakes in future, so that if we draw a line very near to this one, that will be considered as bad because it doesn't provide a good buffer. The other line that is very near to the red class will not be good compared to this one because that line would give no cushion. This particular line is giving a cushion. Let's call that cushion gamma. So W transpose X positive, class A, negative, class B. Okay, but now we want to bring something additional into the mix, and that is this gamma, the distance, minimal distance from the nearest data point. Whatever it is, if we have that in mind, we can make this line more generalizable for future data points. Geometrically, if consider there is a data point xi right here on the dotted line, and we want to take its projection on the W, the class boundary, which is perpendicular to the W, what shall we do? This gamma distance is equal to W transpose X divided by the norm of W, L2 norm. To keep things simple, I'm just ignoring the intercept for now. We can bring in, but later. Let's look at the line as W transpose X, and if we want to prove that gamma will be equal to W transpose X divided by norm of W, we can start by the projection xi hat will be equal to, we need to travel from xi some distance gamma. So from xi we subtract gamma, and we need to travel which direction? Direction will come from W over L2 norm of W. So we either go this way or that way depending on the position of xi, and that comes from W over L2 norm of W, and gamma is the distance that we want to travel towards the decision boundary. If that is the case, and we know W transpose X hat will be 0 because it's the decision boundary. It is the decision boundary because over here W transpose X is 0. If we replace this value in here, we get this. And bringing W transpose inside the parentheses, we get this. Now you can see if we take this term to the other side, this is twice as much the L2 norm, so we cut them, we get L2 norm, which is the square root of sum of W's, and we take this term to the other side, and W transpose X equals gamma multiplied by L2 norm, and we bring L2 norm to the other side, and we get this distance. Visualizing the intuition and deriving the distance, how shall we calculate? So if gamma can give us some benefit for future data points, this is how we are going to calculate it. This is how it will look like. Why do we need this support? To have some cushion to make a mistake in future on the test data points. From the training data points, the points that are near to the class boundary can give us some benefit. And that benefit, I just provided an intuition, can be derived like this. So this gamma is important. So if gamma is W transpose X divided by L2 norm of W, then we can take an arbitrary distance, let's say 1. It could be 10 or 20 or whatever, but let's make it a constraint. It's 1. We want to keep the cushion at distance 1, both sides of the class boundary, so we take the norm. In that case, if the cushion is at distance 1, the new rule will be W transpose X plus B is greater than equal to 1 for the positive class, and it will be less than 1 for the negative class. Makes sense, right? So now we can simplify this rule by multiplying the value of Y with W transpose X. Whenever it is -1, W transpose X will be also giving positive value. So the result will be -1, so it will be misclassified. Other cases, it will be greater than 1 and correctly classified. So instead of writing in 2 lines, we can write the rule in 1 line, just assuming that Y is having -1 or 1 values, binary classification. So Y multiplied by W transpose X, if it is greater than 1, we are good. Either positive or negative class, we are good. If it is less than 1, then we made a mistake. So this particular rule, if you notice, is the Hinge loss that I just showed you. So let's decompose this gamma. So W transpose X divided by L2 norm of gamma, we need to have distance 1. So 1 on left side, 1 on the right side, 1 distance here, 1 here. We can write it as 2 over L2 norm of W. If that is the case, what we want to do is that in addition to classifying the points correctly, we want to maximize this distance. We want to find the dotted lines at maximum possible distance. And since it is in 1 over L2 norm, if we want to look at it inversely, we will minimize L2 norm of W. So minimizing the norm of W, we can just, since it's scale invariant, we can take a square to make it derivable and divide it by 1/2 to make our life easy. We say minimizing this subject to this is going to be the basic concept behind what we are going to do today. So not only we are classifying, but also taking care of the margin. We know margin gamma is norm of W. We are minimizing that to maximize the margin as well as classify things correctly. So we now want to do 2 things at the same time. Before, we had just 1 function. In case of 0, 1 loss, we were just concerned with 1 objective. Find the weights, multiplying them with X. If it comes positive, class is positive, truth is positive, we are good. Those weights are good. But now, that particular objective is augmented with another objective, getting the margin maximized. Maximizing a function, we do what? Consider on x-axis we are having some values for x, and fx is the function here. We'll take first derivative. That will give us either of these 2 points. On these 2 points, the rate of change of this function is 0. But we are concerned with minimizing. So how do we know if we are on minimum point or maximum point? Which one are we on? By taking first derivative, we cannot decide. So we take second derivative. If second derivative is negative, we are on maxima. That means beyond this point, the rate of change is negative. If the second derivative is positive, that means beyond this point, the rate of change is going to increase. After it became 0, now it will change to be positive. So to first and second derivative, let us know for a given function which point is minimum or maximum. So using this, we will do something, but we are not dealing only with 1 function. We are dealing with the function with some constraints. So we are trying to minimize a function that is subject to some constraints. Constraints could be gx equal to something, or inequality constraints, which is hx less than or greater than equal to something. This kind of problem we want to visualize would look like this. This is your function fx, and this is the constraint. Minimum of fx is here, but given the constraint, the only feasible solution is beyond 1. We can have 2 constraints, so the feasible solution will be between these 2 constraints. We will minimize the function and that value will be subject to G1 and G2. So this area, the minimum value is here. So our function subject to constraints would look like this. And constrained optimization, the framework to solve these problems, is offered by Lagrange through this Lagrangian equation, where we put the actual function that we are trying to minimize plus the constraint multiplied by a scalar if there is only one constraint, a vector of different lambdas if there are multiple constraints. It works magically as long as there are some conditions that are met. So this equation formulation itself is called Lagrangian function. Lambda, gamma is the Lagrangian multiplier, lambda, and g of x is the constraint function. There could be many. Fx is the function that we are trying to solve in terms of minimization or maximization, and x is our x. What we really get out of this formulation is that both fx and gx have, they point to this, their gradients point to the same direction as long as gx is following some conditions. And it's just a scalar multiple scaled by this particular Lagrange multiplier. After that, after multiplying it with the gradients become same, they point to the same direction. Or we can also say if x is minima, then the partial derivative of Lagrangian with respect to x will be 0, and with respect to lambda will be 0. If that is the case, and fx is convex, in that case, it's kind of loop back to this reality. How? If fx is convex, then on this point where x, Lagrangian partial derivative of Lagrangian with respect to x is 0 and with respect to lambda is 0, then that particular point x will be minimum. But the condition is that fx is convex. You can loop back to the particular image that I showed in the beginning. So we are trying to now go to this particular loss function. We were not happy with this one because it's not differentiable. Secondly, the farther the point is from class boundary, the loss or benefit is same. So we want to use this one, Hinge-like loss function. In this particular formulation, we geometrically looked at on 1 minus y multiplied by w transpose x gave us the decision, positive or negative class, and the loss function will be the maximum of either 0 or this value. So if it is not 0, then loss will be this much, and this is this arm of the hinge. If it is 0, we correctly classified, then we don't worry about this part, to 0 loss. So we will keep this in mind, and we will try to come back here in the general constraint optimization. So we benefit from this Lagrangian formulation, which has this property. Number one, the derivative of fx and gx point to the same direction. And x will be minima as long as fx is convex. And we just looked at the hinge loss, and the reason why we need to, for the hinge loss to be convex, because we want to use Lagrangian formulation to find the minima of our function with some constraints, the constraints of having maximal margins. And yeah, that is the basic intuition. And the how shall we do this is we will solve some few examples that are kind of going to help us further our understanding of how constraint optimization work. But this particular Lagrangian formulation is subject to some constraints. First, x star that we are looking for is going to be minima if and only if the derivative of the Lagrangian with respect to x and lambda is 0. This condition and with respect to x, the constraints are negative and lambdas are positive. And second derivative is positive. If there are multiple constraints, this will be a matrix, and that matrix is having positive values. If you remember, in the previous sessions, we used this matrix of second derivatives for the independent features, we called it the Hessian when we were doing logistic regression. So Hessian being positive semi-definite makes sense because we want to find the maximal point of the function. And this particular constraint is something that is very intuitive. Lambda, if it is greater than 1, greater than 0, that means corresponding constraint is active and that will be 0. Only then we get 0. If lambda is negative, that means the other part, dx, the corresponding constraint, is not active and the result is 0. We call it the complementary slackness. These 5 givens or constraints or points that should be true for a Lagrangian to be solvable and to have a solution are called KKT conditions. We need to meet these conditions. First, there is a point where given x and lambda, first derivative or the differential of the Lagrangian is 0, and other conditions. 5 KKT conditions. If they hold, then we can find x star. Before we do the actual classification problem, let's exercise a few of the examples that will cement our understanding of how a function with constraints can be solved together. So this is our function with 2 variables, a quadratic. It is subject to this condition gx. If we try to put it in Lagrangian formula, we will put the function first minus the lambda multiplied by the constraint. Now we can solve it by taking the first, checking the gradient with respect to x, y, and lambda, and the gradients would look like this. So 2x minus lambda will be the gradient or partial derivative with respect to x. With respect to y, it will be minus 4y minus 4 minus y. The other terms are constant, will go away, equals 0. And then with respect to lambda, it will be x plus y minus 0. Other terms are constant, will become 0. Keep it here and substitute values. First, we solve for x and y in terms of lambda and put those values in x plus y minus 1. We get lambda and we got the solution for f. This is the x 4 by 3, where this particular function is minimized, conditioned on or subject to this constraint. There is another way. The other way is that instead of taking partial derivative of the Lagrangian with respect to x, y, and lambda, we just look at the derivative with respect to x and y. And we represent x and y in terms of lambda and form a new equation. So this particular equation, wherever we see x and y, we replace it with minus lambda by 2, minus lambda by 4. We get this one. And this particular equation is only in terms of lambda now. So the original variables x, y are now eliminated. The first derivative of this particular function should be equal to 0 and will give us lambda. Replacing this lambda here will give us x and y, and we reach to the same solution that we got with solving 3 equations. What we are reaching at is we have just one constraint, 2 variables instead of 2. If we had 200 features, it's a humongous problem in that case. But if we can turn it into this form, we are solving our problem in terms of only one variable, in terms of the constraints. This intuition is very important. So even though this example has 2 independent variables or features, let's say, but the constraint itself, if we can transform it using the Lagrangian framework into, we can write it like this. So everything we look at is in terms of the constraint variable that we are going to call it something special. I will tell you what is it. But in that case, our life becomes easier. So this is the simple example that we solved. Original problem, minimizing this function with respect to this constraint, is primal problem. Primal problem has so many variables and constraint variables. If we turn it around and look at it in terms of lambda, we are going to call it Q function, Q of lambda. We want to maximize this Q of lambda. The only thing we need to make sure is that the second derivative of this particular first derivative is negative. That means we are sitting on the maximal point. And that is the only constraint. So if we want to maximize Q of lambda, So here we are solving for just one variable. And the constraint on this is not the constraint. We are representing Q of lambda using the original equation. And this particular formulation we are going to call the dual formulation, dual formula, dual function, or dual problem. So original problem is primal problem. The variables we have in original problem are primal variables. When we turn it around in terms of the constraint variable, it becomes dual problem. We call this variable the dual variable. We solve the equation, dual function equation, in terms of dual variable. And you can guess where I'm preaching at. In the beginning, I started the story by having our original equation of classification y w transpose x. I said it's greater than or equal to 1, it will solve our life. Now we have a constraint there. We also want to minimize the norm of w. Can we put that in terms of Lagrangian? And instead of solving a big problem, we'll be solving a small problem in terms of w only, norm of w. I'll take a break and let you think what we are saying here. And let me know, how do you feel about this concept? Lilith?
How am I feeling? My brain is melting a little bit. But
I will repeat then. I will repeat then.
Mhm.
So just stop me and ask me to repeat. I'm going a little fast maybe, but this particular example is maybe a good point where we can stop and redo it again. Let's redo it again. Actually, let's do another example. We had just one constraint. Let's put multiple constraints. If we have multiple constraints, original function subject to multiple constraints will look like this. We will have many lambdas, each for each constraint. We will sum them, sum the multiplications, and Lagrangian says you will get the minimal x if given those KKT conditions. And we can use it for our benefit. Another simpler quadratic example is x squared plus y squared. The same ball-shaped function, but constrained to x plus 1 and y plus 1. We have two constraints now. In the original primal solution way of solving things, we will take derivative of the Lagrangian with respect to x, y, lambda 1, and lambda 2. With respect to x, the derivative is 2x minus lambda 1. Let's put it in this way. So Lagrangian format will be x squared plus 5 squared minus lambda 1 into x plus 1 minus lambda 2 into y plus 1. All right, we first, the gradient of this equation will be equal to 0, KKT 1, condition 1. If that is the case, we take the first derivative with respect to each independent variable and the constraint variables, put them equal to 0, and solve it one by one. Okay, x is equal to minus 1 from here, y is equal to minus 1 from here. And then we put minus 1 and for x and y in these equations and solve for lambda. Okay, life is good. And then we put back these values into this equation and get f equals 2. So 2 is the point that Lagrangian promised us we could find through this formulation. Okay, but the alternative way is that instead of looking at the differentials with respect to lambda 1 and 2, we just look at the partial derivatives with respect to x and y of the Lagrangian. They will give us x and y in terms of dual variable. We put those back into the equation to create dual formulation of Lagrangian. So x squared is lambda 1 squared by 2, y squared is lambda 2 squared by 2, minus everything same. Wherever we see x, we put lambda 1 by 2. Wherever we see y, we put lambda 2 by 2. And our q of lambda becomes this. Dual formulation says the gradient of this particular equation, the function, will be also equal to 0. If that is the case, in that case, with respect to lambda 1 and lambda 2, we see the values for lambda 1 and 2 are like this. And we can also check the second derivative will be negative. We have negatives here. So 2 lambda 1 square, 2 come down and it half the 4, so 1 by 2 lambda 1. This 2, when we took the derivative with respect to lambda 2, it came down and half the 4. We get 1 by 2. Sign remains in lambda 2. 2 and lambda 1 squared by 4 are constants when we look at this with respect to lambda 2. So they become 0. So this is the first derivative. Second derivative will be -1. So negative derivative. Second derivative means we are standing on maxima. Okay, we are good. So lambda 1 and lambda 2 minus 2, we put them back here. We get our original f that we solved primal way, but primal way is expensive, more difficult, computationally exhausting if we have hundreds of independent features.
So doing it the way with the lambdas is the less computationally expensive way. Is
It's
basically what we're doing.
inexpensive. Inexpensive. Like we are looking at only one variable. Instead of looking to optimize many things, we only have now one function with one variable, and we can see where it gets minimized. And if that point second derivative is negative, then we are standing on maxima of that function, and that is what we want. We want to maximize the margin.
All right. So the solving for the lambda is the
Better
point of
way.
this. Yes,
Yeah.
okay.
The dual formulation, dual problem. Primal problem, we can turn it around into dual problem, and that is simpler to solve. So going back to the basics, textbook says any function, if we want to minimize subject to some constraints, we can put them into some formulation called Lagrangian. Lagrangian can be solved primal way. This is the primal formulation, and we can do then dual formulation. And for this particular problem, primal solution is this, and for dual, I would invite you to solve this particular function subject to these two constraints. It's a little bit more complex, like cubic, but when we put it in the dual formulation, we will have the same luxury of looking at only one thing and minimizing it. So the dual problem and the primal problem are related, right? So we are having only two variables to just have a luxury of understanding here, but when we ask machine to do this thing for us, we have hundreds of variables, right? Let's say we are dealing with an image, 250 by 250, huge number of features. The thing is that primal problem, we want to minimize the hinge loss function that we looked at in the beginning, looking like hinge. Dual problem, we maximize the constraint function to get lower bound on the primal problem. Visually, I want to show it like this. This is our primal problem. This is the constraint. Lower bound on the primal problem is constrained by the upper bound of the constraint function. This is the infimum or minima of the function we want to minimize. This is the supremum or maximum. Greatest lower bound of the original function and the smaller upper bound of the constraint. They are related. How? Argmin of this function is equal to argmax of this function. Because red function is constrained by blue one. The minima of this function is not the solution. It is constrained by this one. We cannot go beyond above this value. Above this value, the region is not feasible. Only feasible region is here. If there is a gap between the minima of function we are trying to minimize and maxima of the constraint, we call it the duality gap. And the duality is weak if we put both in one equation and the Q of lambda terms. So the maxima of Q of lambda will be always less than the minima of f of xy. Let's say x is x. This is just two-dimensional function here. Then, if there is no gap, so maxima of this meets the minima of the original function. Maxima of constraint meets the minima of original function. Zero gap. Then we have strong duality. The duality gap is one thing that we need to take care of. And if it's strong duality, the optimization is simplified. Number of constraints, as long as they are less than number of features, our life is easier. Dual variables also provide further insight. Just look at our solution. The perceptron or logistic regression solution is lonely line or hyperplane. But if we constrain our solution with some buffers or two additional dotted lines that I showed you, we have more insight now into the future. We can say we are safe from making less mistakes, more mistakes on the test data. If the line is blind line, just a line that is a line there, and it doesn't give us any insight how it will behave in future. But with the constraints, we have a buffer now. We have more insight how the machine will behave in future. Or if an AI agent learns just a line and the other agent learns a line with constraints, we will choose the second one because the second one has some bumper, right? The dual problem is always concave, even if the original one is not. So the second good benefit is that when the things are concave, there is only one global minima or maxima, then we can use gradients to solve. And that is why Lagrangian has two interesting, powerful benefits. If feasible, the solution is simpler. And second, even if the original problem is, primal problem is not concave, Lagrangian says, guarantees that the dual will be concave. So again, subject to these constraints, number one, there is a point x and a value for lambda that is where the gradient is 0. If there is, then we can solve this. This is condition number one. If there is no such point, we are just, there is no chance then. But if there is, Lagrangian is bound to find that. Second, this is the condition, second KKT condition. We call it the primal feasibility. So and the lambdas are greater than 0. And the second derivatives are positive, or Hessian is positive, and the complementary slackness. Given these 5 conditions.
I have a question.
Yes.
The equations that we were solving before this, when we were solving the dual for the lambda, were these conditions already in place when we were solving that equation, or was the solving of that equation, how are those related?
So they are related. If we solve this particular problem, which is subject to G1 and G2, primal way is that we know if we put it in this formula, Lagrangian function, then the gradient of this function will be equal to 0, and we take partial derivatives and solve all, substitute and find the solution. So this is way number one. The alternate way is that instead of taking partial derivative with respect to everything, we just take the partial derivative with respect to the primal variables, the independent variables that we have, the features x, y here, x and y. The dual variable we will solve, will represent x and y in terms of the dual variables and substitute in the original equation so that we can turn it into dual format, dual function. This is the same equation as this one.
Right. My question though is, let me see if I can rephrase it. Are the constraints implicit in solving of these equations?
Explicit. Constraints are provided.
Okay.
Constraints are functions. We visualized them here like this. So function 1, function 2, they are provided, not implicit. So before today, we were just looking at a loss function and trying to find the minima in terms of logistic regression. But now we are constraining it with some other functions. So the feasibility region of the solution is now constrained. We cannot say this is the minima. No, this one is the minima.
Okay, so we're trying to solve the red part that's within the constraints.
So within the constraints. So everything is given. In the story that we started from is here. So we said, we agreed that y multiplying y with w transpose x, if it is greater than 1, we are good. We made the w is good to make classification correct. If it is less than 1, then we made a mistake. That was our objective till last week. Now we are having an additional thing there. We want to minimize w, norm of w. And we looked at it geometrically, why norm of w is equal to the gamma, the distance, this cushion vector, this dotted line. So we are not only worried about finding out the w that represents, that is perpendicular to this line, we are also putting it, in addition, we are saying, okay, let's constrain. We want only the line that gave us these dotted lines in best possible way. 2 additional constraints. On the right-hand side, we want something. On the left-hand side, we want something, a bumper, a cushion. Got it?
Yep. Thank you.
Then it becomes very easy. But I on purpose included these examples just to freshen up your memory for Lagrangian optimization, constraint optimization with respect to these 5 conditions. If these conditions meet, we can represent a function in terms of constraint variable or the dual variable, which will make our life easy because constraints are always going to be few, 1 or 2. Independent variables will be maybe hundreds or thousands. So we come back here.
Features are a lot, lots of features.
Right. So even though we are showing on the slide a toy example with 2 features, but just imagine if there are 200, the constraint will be still simpler and fewer constraints than the number of features. So yeah, here we go again. If gamma, the distance between boundary and the cushion that I'm saying, is W transpose X by the norm of W, in that case, we want to maximize 1 over norm or minimize norm, and we put 1 over 2 and square it just for the make it fun because we want to differentiate it. It's scale invariant. If we scale it, like take a cube or whatever, the line will stay here. We will get the same results. So to make our life happy, we square it and multiply it by 1 by 2 so that when we take derivative, we just get W. 2 will get cancelled too. And subject to the equation that we had, original classifier equation, W transpose X multiplied by Y should be greater than 1, our life is happy. So we will put that in the constraint part. If we bring 1 to the other side, it looks like 1 minus this, less than equal to 0. And this is exactly the story that we were playing with in Lagrangian formulation thing. This is the original function, prime, and this is the constraint. Together, they become Lagrangian function. And this is the primal way, primal problem, right? Primal problem will look like this. Let's take derivative of this function with respect to W, B, and lambda. But what we want really to do is that represent this in terms of lambda, make it dual. And if we do it primal way, with respect to W, when we take derivative, 2 cancels 2, we left with W only, and from here we are left with lambda Y multiplied by X. And Lagrangian says it will be 0, equal to 0, the partial derivative with respect to W. And that means W is equal to summation of all lambdas, all Y's, and all X. Oh, some insight. Let's put beta, the B, the intercept into mix. With respect to B, this term will evaporate, and we are left with minus summation of lambda YB, because W will go away, lambda YB, and 1 will go away as being constant. And that means we can take B out, and minus B it means nothing. It goes to the other side of the equation. So lambda Y multiplication and summation is going to give us the B. So this was the primal. If we put it in dual function, it will look like this. The dual representation subject to lambdas are greater than 0 and B is equal to 0. B, we solved B for multiplication of lambda and Y and summed up. So these 2 are the constraints on the dual problem. And we can now see that everything is in terms of lambda, summation of lambdas minus, this thing. These are just the constants, right? We have the x's, the values, the lambdas are there that we need to solve this for. And when we look at our complementary slackness property, where we say lambda and the constraint, when one of them is 0, the result will be 0 only when one of them is 0. So for all the lambdas that are non-zero, gx corresponding constraint will be inactive, so that it becomes 0. That means for all the non-zero lambdas, corresponding x will be the one that is on distance 1 from the class boundary. And that particular instance, that particular data point will be able to calculate W for that data point using, we just solve W as being equal to summation of lambda I, yi, xi, their multiplication. So that particular point where lambda is non-zero or positive is going to be our important thing that we started our story today for. till now, the sign of W transpose X plus B gave us the decision if we are in blue class or red class, plus class or minus class. Now, W is, we said through solving the Lagrangian, we came to this conclusion W equals to the summation of these quantities, multiplication of these quantities, and we put the value of W here now. This is the thing, the inner product of X that is new today. So lambda multiplied by Y multiplied by X, when it goes here in place of W, it becomes this. This particular thing is going to be very useful from this point on, and we are going to call it a special function that will help us not only today we got the cushions, we got these cushions, dotted lines, the best possible boundary with cushions, we got it. But this particular dot product of x's is going to help us solve nonlinear classification problems. We will see how, but this particular formulation, we are going to transfer from this. We can visualize W transpose X plus B now very easily, but this is transferred to this one that is going to be our bread and butter from now on. In this inner product, we will talk about it so many times, you will get sick of it, but this is the thing that will give us the cushions. Now I'm going to give them the name. Wherever lambda is positive for that particular data point, we will guarantee that it is distance 1 away from the decision boundary, and that data point we are going to refer to as support vectors. And the algorithm, that the derivation and the solution that give us support vectors of a linearly separable binary data set. Those data points give us the support vectors. So we don't look at the class boundary in terms of W transpose X plus B anymore now. We look at the class boundary in terms of the inner product multiplied by Y and lambda plus B. Once we have that, for prediction, we can use, we don't need Y, just use the inner product plus B and lambdas, and we get nice formulation of support vectors. We look at the class boundary in terms of support vectors now instead of the hyperplane W transpose X plus B. So we traveled from 0-1 loss, looked at the quadratic kind of squared error loss. It was not sufficient. We looked at the logistic regression last week. Today we had a geometric kind of visualization and interpretation of the Hinge loss. 1 minus yi W transpose X will give us the decision. And if we plot that, it looks like a hinge. We use that hinge loss. We also visualized the geometric and functional concept of margin. Looked at a few examples of constraint optimization and found out how to derive optimal margin classifier. And later we called the data points that are guaranteed 1 point away from, 1 distance away from the class boundary. Instead of using W transpose X plus B, we are going to use those data points to estimate whether we are in class 1 or 2, -1 or +1, and that is going to give us a luxury of having a safety bound for the test data. Support vector machines. That is, for now, we dealt only for the linearly separable things, but we will see how support vector machines can solve non-linearly separable data for us as well. And that is coming, but the basic concept will remain the same. So we are transporting our understanding from W transpose X plus B to the support vectors. So this was what we had for today. The mic is yours now.
So could we go back to the equation where we had the notation for the support vectors? X transpose comma X. This one's 2 slides back, maybe? Yeah, right here. Could you explain again the X transpose comma X? Is that
the inner product of independent features?
So that's the dot product between X transpose and X?
Right.
Okay.
Where it came from? we replaced W now. W was not good enough for us. From Lagrangian, we derived that W is equal to the summation of these quantities multiplied, and we replaced them here. So lambda y, this is the inner product of X transpose X. B will live as it is. It has like limited role here. So now we are going to live with this formulation.
Right. So the X transpose, so that dot, the support vector part of it is what gives us the dotted lines, the dashed lines.
That's
the
right.
buffer. Perfect.
That's right. And that is defined by the points. This blue point, or too big, but just imagine it is the point that is one distance away from the line to the right side in this red. So these, instead of having W transpose X, we will live with these 2 points.
Right.
And these are enough in future when we want to classify for test data. We will forget about W. We will use these 2 points to classify because they are support vectors. The boundary is between them. So we drop the boundary. We keep these 2 points now. If thing is on the left of this point, it's class A, right of this point, and class B. Otherwise, it's a mistake. So it's now hard margin. We didn't talk about what if some test data, the points come here.
Yeah, I was just going to ask that question. I was going to say, well, what if there's a point that's actually inside the boundary?
So we have now a notion of soft margin. This is the vanilla solution for support vectors. In soft margin, we allow, okay, make 10 mistakes out of 1,000. It's okay.
Okay.
And that makes, we still work with support vectors, but with soft margin, we allow a degree of being wrong and then find the support vectors. This thing never worked in reality. In reality, classes are overlapped and finding the best angle is almost impossible. So we have soft margins in practice, but to understand the concept first, we just put things apart and so that we can draw support vectors. So we do allow mistakes. How many mistakes? If we go this way, 20 mistakes, this way, 10 mistakes. So less number of mistakes will be the solution.
And does this allow for nonlinear boundaries?
Not yet, but soon we will see that this particular guy, X transpose X, enables us to put our nonlinear problem linearly separable way. We will see how the inner product can transport our data into a new domain where we have more features, but with more features, the data becomes linearly separable, and then we do the same linear classifier or support vector machine algorithm. But we will see that we're going to call it the kernel trick. So this is going to be our kernel that will transform our data into higher dimension. In lower dimension, 2 things are overlapping, but when we look at add another dimension, they are separable, right? So just like that, we will see soon.
Okay, thank you.